Hello dear friends, welcome back to my channel. I'm Gerard and I'm here to revise matrices. Matrices, so far we had 3 videos on matrices. So we have defined many different terms. For example, we have talked about augmented matrices and reduced row echelon matrices, and we also look into what's the Gaussian elimination method and the Gauss-Jordan elimination method. And after that, we have also talked about the arithmetic operations that we can carry out with linear equations or a system of linear equations, and we have seen how we can add, so do addition and subtractions with matrices, and we have also done multiplications of matrices. We know what's a coefficient matrix, and today we'll talk about square matrix as a start, and then we'll try to do operations such as finding the inverse of a matrix. So let's do that. First, we are going to define what's a square matrix. So let's say we have a matrix which is square. A quadratic matrix is one which is of the same size for the row, the number of rows, and the number of columns. An example here is 2 by 2, 3 by 3, or 4 by 4, and so on. So these are quadratics matrices, and they can also be called a square matrix. So if A is a square matrix, so I have A here with capital uppercase letter, and if matrix B of the same size, so it's going to be of the same size. So if A is 2 by 2, automatically you have a matrix 2 by 2 for the matrix B. And so it's very important that these two matrices are of the same size. So they are of the same size, and if you will make the product of AB, and AB is equal to BA, so I have now to point out that matrices are not commutative. So you cannot change the place of the matrices and think that you will yield the same result. So only if, sorry, let me erase this. Only if this is the case, that they are somehow commutative in these particular cases, then it is these two products of matrices A and B is equal to I. So what is I? We'll find out in a moment. So I is an identity matrix. So identity matrix. I is an identity matrix. So we have square matrix. We have two square matrices of the same size. We have the products, and we also have their kind of a reverse product of these two matrices, and they're all equal, and they are hence equal to the identity matrix. So B is called an inverse of A for that reason. If this equation or this property is in force, therefore B is the inverse of A. As we have seen previously, so to denote the matrix A, we use a capital letter, and if we want to denote the inverse of this matrix, we're going to use such a notation. So this is the matrix, and this is its inverse. So inverse. So since matrix B is the inverse of A, so it's going to be like this. So we have come to the conclusion that if you have the product of a matrix with its inverse, you're going to get an identity matrix. So an identity matrix looks like this. So we have seen the leading ones. So it looks almost like a row, a reduced row echelon form matrix. All right, so let's do an example so that we can understand. So now we are understanding what's the inverse of a matrix and the relationship between the product of a matrix with its inverse, and that it yields. It doesn't matter if you take the inverse, you multiply it by the matrix, or you take the matrix multiplying by its inverse, you will still get the identity matrix 1 0 and 0 1. So let's do an example. We have AB is equal to 2. So this one is A. A is a quadratic matrix with 2, minus 5, minus 1, and 3. And we're going to multiply it with the inverse of A. So just as a reminder, once again, B is the inverse of matrix A. So we can write it like this. And we have now this product. And if we use our principle for multiplication of matrices, we will have the row multiplying by the column. So we're going to have 2 times 3 plus minus 5 times 1 is equal. So we have 6 minus 5, which yields 1. So we can write here 1. And now we're going to have 2 times 5 plus minus 5 times 2. So now we have 10 minus 10, let's give us 0. And taking the second row, we have minus 1 times 3 plus 3 times 1. And this is equal to minus 3 plus 3 is equal to 0. So this is not surprising, because slowly but surely we are going to get the identity matrix. And the identity matrix is composed of ones and zeros. So we have done this and this. So the last one is going to be minus 1 times 5 plus 3 times 2. This is minus 5 plus 6, and you're going to have 1. So for that reason, we can say that matrix B is the inverse of matrix A. So let's analyze the two matrices now, so that we understand how we can transform a matrix into its inverse. So first of all, here is the main diagonal. As you can see, we have swapped the places for the entries on the main diagonal. The second observation that we can make here is that for the, I think we call it the back diagonal, we see that the signs of these entries have been changed. So it's the inverse of what we have in matrix A. So which means that to change a matrix which is obligatory a square matrix into its inverse, we have to swap the entries along the main diagonal and change the signs of the entries on the back diagonal. So which brings us now to some exercises how to practice this. And so we'll have a generic way to transform a matrix to its inverse, into its inverse, sorry. So here I have another subtitle for this video: matrix with no inverse. So even if a matrix is quadratic or it's a square matrix, it's not obligatory that this matrix has an inverse. We'll take as an example here A, which is 1, 2, 3, 4, 5, 6, and then you have 0, 0, 0. So bearing in mind that these entries are actually three equations, linear equations, and their results are equal to zeros if it's not a partition matrix. So normally you have here the other side of the equal sign, and they should be homogeneous, remembering this this rule, the homogeneity rule or theorem if you want. So it means that they have to be consistent. So the system of linear equation is consistent, which means that they have solution. They have a solution set. Okay, so this is the first observation that we can make here, is that we have zeros on the left, on the right, sorry, of this system of equations, and okay, so let's do an example. We know that we are going to have a look at matrices that are without an inverse, so they have no inverse. Let's have a look at this matrix: 1, 2, 3, 4, 5, 6, 0, 0, 0. We have another square matrix, which is B, and this time we're going to use just for coefficients B. So we have B11, B12, B13, B21, B22, and B23. And remembering that they have both to be of the same size. So here we have 3 by 3. So it has also to have 3 rows and 3 columns. So we have B31, B32, and B33. So what we're going to do now, we're going to make the product of A and B, and we're not going to do it as we did before. We're going to use the linear combination, sorry, the linear combination. So to make it easier, I'll just rewrite it. So it's going to be B11, times 1, 2, 3, and then you have B1, 2 times 4, 5, 6. We have B1, 3 times 0, 0, 0, and so this is the first entry. So we have to do for all of them. So this will just give us the first row of the product. So what I can do is write all of them just like that. B21 times 1, 2, 3 plus B22 times 4, 5, 6 and B23 times what we have there, 3 zeros. Notice that we are losing these values here because they are being multiplied by 0, and we have 2, 3, 1 times 1, 2, 3 plus B32 times 4, 5, 6 and B33 times 0, which gives us 0. So now that we have written the multiplication this way using the linear combination method, we're going to erase what's at the top because we already have those those data down here, just to make some space. And so let's see what we'll get as a result. So this is the product AB, and we have a new matrix which is also the same size as matrix A and matrix B. So where is it? Just a moment. And so I'm just going to write it like this. So if you take B, you're probably going to get B11, B11 plus B, so 1B, 2B, no, that's not the way. Okay, so I understand that this addition is going to come here. So I try to add them, but so the coefficient B11 times 1 and the coefficient B11 times 2, same coefficient times 3. So you plus the coefficients here times 3. Normally you will have a number here and you will be able to add them up. So the result, the sum of it is going to be here. And you do the same thing for the second row and the third row, which will leave you in the end with a matrix of the same size as A and B, which means 3 by 3, a square matrix hence, and it should give you, if you reverse the product, so instead of doing the product of AB, you do the product of BA, so you will get another matrix. So now just to make it clear, if you take AB and if you take AB or BA and you get in the end a square matrix, an identity matrix 1 0 0 0 1 0 0 0 1. It means that B is the inverse, sorry, not like this, but B is the inverse of matrix A. So, but because we had in matrix A, uh, we had zeros here, so it will not be possible to have the identity matrix. And for that reason, we say that A does not have an identity, does not have an inverse. So the goal of this was to prove that some matrices, they have no inverse because of their homogeneity, if you want. So if the sum of all the coefficients is equal to 0. So just to summarize here, so if you have any matrix, of course a square matrix, because we want to find their inverse. So if you have something like this with zeros at any column, so you will not have an inverse. This will not exist. So there is a sign in math that I think it's something like this, means that it does not exist. Okay, so that was about the inverse of matrices. I'm going to pause the video and we're going to look at some other examples. Okay, so we're almost midway in this video, and this time we're going to find the inverse and we're going to work with the identity matrix. So we have the matrix inverse as a subtitle, and if we have, as we proved, if we have a matrix multiplied by its inverse, you get the identity matrix. So it doesn't matter if you have the inverse multiplied by the matrix or the matrix multiplied by the inverse, so they are commutative, you will still get the identity matrix. So one of the properties that you can take here is that if B, for example, and C, they are both inverse of A, or inverse of A, hence, so we can first say that B is equal to C, because they are both inverse of A. So why is it important to have the inverse of a matrix? So the inverse of a matrix is going to help us later on to solve polynomial expressions. And this property of having a matrix multiplied by its inverse, yielding the identity matrix, is going to help us to carry on those operations. So as you can see here, if you multiply a matrix with its identity or with an identity matrix, you get the same thing. You get the metric itself. It doesn't matter if you take the matrix, you multiply it by the identity matrix, or you take the identity matrix, you multiply it by the matrix, you will still get the same result, which is the matrix A, for example. And as we have concluded from the previous workout, so if we have a matrix, let's say A, B, C, D, which is a square matrix of 2 by 2, the inverse of it is going to be, so first we have a look at the main diagonal. We have to swap the places, so D is going to be here, A is going to be here, and we have to change the sign of the back diagonal. So if they are positive, they're going to be negative. So this is the inverse of this. Some other properties of inverse of matrices is that if you have a product, you make its inverse, it is equal to the product of the inverses of these matrices. Hence, it doesn't matter if you make the product first and then you inverse it, or you inverse each product and you make the product. So we are here able to demonstrate this with an example. We have the product and then we inverse it, and we also have the inverse of each of the individual matrices. If A is 1, 2, 1, 3, and that B is 3, 2, 2, 2, so let's do the product. We're going to get 1, 2, 1, 3 times 3, 2, 2, 2. We can proceed by how do you call this? Just one second. So linear combination. So if we proceed by linear combination, we're going to have 3, 2. Is it 3, 2? Yeah, 3, 2. And then 1, 1. I think I'm mistaking here. Plus, yeah, I'm mistaking here. Let me rewrite it. So it's going to be like this: 3, 1, 1 plus 2, 2, 3, and we have after that 2, 1, 1 plus 2, 2, 3. So what do we have here? We have 3 times 1 is 3 plus 2 times 2. We have 5. So 3 plus 4, it's 7 actually. And 3 times 1, 3 plus 2 times 3 is 6. 6 plus 3, 9. And we have 2 times 1, 2 plus 2 times 2, 4. So that's going to be 6. 2 times 1, 2 plus 2 times 6, 6. 6 plus 2, 8. So the product of AB is thus 7968. So if we want to have the inverse of this product, we will follow the same rule that we used before. So we'll have a look at the diagonal, the main diagonal, and we're going to swap the places, and we change the sign of the back diagonal entries. So we have come with the first result, and if we keep this here, and now we try to make the inverse of each matrix, and after that the product. So once again, A is equal to 1 2 1 3. So the inverse of A is going to be 3 1 here, minus 1 minus 2, and if B is equal to 3 2 2 2, the inverse of B is going to be 2 3 here, and minus 2 minus 2. All right, so now let's do the product of both inverses. So this is minus 1, B, and so we're going to use the linear combination. So let's rewrite this here: 1 2 2 1, and 2 minus 2 minus 2 3. Okay, so using linear combination, we are going to have 2 times 3 minus 1 plus minus 2. I'm sorry, just a moment. So we have minus 2 here times 2 1, and after that we have wait a second, minus 2, yeah, 3 minus 1 plus, finally we have 3 times 2 1. So if you look here at these entries, it should be the transpose of the inverse of B. So just to be sure, so changing this into here, it doesn't make any difference, and so this here, and this here, and this here looks good to me. So let's do the addition. So 2 times 3 6, plus minus 2 times 2 minus 4, 6 minus 4 2. So we have 2, and 2 times minus 1 minus 2 plus minus 2 times 1 is going to be minus 4. Am I mistaking here? Just a moment. So just a moment. This is AB and this is BA. Yes, I'm mistaking because I don't know if I wrote it here or there, but what we have to find is not, this is not the same. So the product of AB, the inverse of the product AB is equal to B inverse times A inverse. Notice the order here. So they are not commutative. So we have to inverse the places. So we're not going to make this product, but we have to put B at the front and A at the back. So we have to start over again. Okay, we have the inverses here. So what we have to find is B1, the inverse of matrix B times the inverse of matrix A, and not the inverse. So let's do this. 2 minus 2 minus 2, 3 times 3 minus 1, 2, 1. Using the linear combination, we'll get, this is 3, is it 3? Let me see, yes, that's 3. So we're going to get 3 times 2 minus 2 plus 2 times minus 2, 3. And we'll get so minus 1 times 2 minus 2, and we'll have plus 1 times minus 2, 3. So let's see what we have here. So we should get exactly the same as here at the bottom. So 3 times 2, 6, plus 2 times minus 4. So 6 minus 4. Is it correct? Just a moment. Here I'm not totally convinced. And that's 2 here. So it's going to be 6 plus, is it 1 here or 2? Let's have a look. This is minus 2, minus 4, 1. So let me check from my notes as well. I have inverse of A is 3, 1. Yes, that's correct. That's good. And this is 2, 3 minus minus. There's 2. This is correct. Looks good. And this also. Yes, there's a minus here. That's why it was not good. So minus here. So which means that you have 3 times this plus minus 1. Should be minus 1 or minus 2. It's minus 2 here. Okay, so let's start over again. 3 times 2, 6 plus minus 2 minus 2, which gives you 4. So 6 plus, is it 1 or is it 2? I will have to pause just a moment. I think I'm lost. Okay, so looks like I found the error. Using linear combination, it's always difficult for me, but I'm getting used to it slowly but surely. So 3 times 2 is 6, plus minus 1 times minus 2, it gives you 8. 3 times minus 2 is minus 6, plus minus 1 times 3, minus 3. So it gives you minus 6 plus minus 3, minus 9. And so here we have minus 2 times 2 is minus 4, plus 1 times minus 2. So minus 4 plus minus 2, this is minus 6. Minus 2 times minus 2, 4 plus 1 times 3, 3. 3 plus 4, 7. So as you can already see here, we have 8 and minus 9 and minus 6, 7. So we have just proved that the product of AB, the inverse of the product AB is equal to the inverse of B times the inverse of A. Alright, so that was just the proof of this property, and the next topic that we will treat in this video is linked to the powers of matrix. So first, just for you to remember that if you have any number to the power, or for example, if you do the product of these numbers to the power r and s, you will have to add them. And how about if you have r a to the power r in a bracket and you have s outside to the power of s, you will have to multiply them. Okay, that's a very basic indices, and the inverse of a is invertible. This is a given. Let's say that it is invertible. So if you have a inverse, you inverse it, you will get the matrix A. And you also have the property that any matrix to the power of n is invertible, I meant. And if you do the inverse of this matrix to that power, you can say that it's the same as taking the inverse of that matrix, putting it to that power. Should give the same result. And finally, but not least, I'm going to make some space here. So we have to know also that a matrix to the power of 0 will automatically give you the identity matrix, which is something that looks like this, if this is 2 by 2, of course, but it should be a square matrix. Okay, so there is also another property that, I'm sorry about that we are going to look before moving on with some examples. So this is the matrix with the coefficient k. Actually, it's not a coefficient. Yeah, it is a coefficient. It is a coefficient. Ka is invertible. So the matrix Ka. So k can be taken out of the matrix. We have seen multiplication of matrices. We have also seen coefficient multiplication. So let's say we have 2, 1, 3, 2, and this is matrix A, and this is K. So if we do the multiplication, we will end up with something that looks like 2K, 3K, 1K, and 2K. So when it comes to powers now, let's say we have done the product of this coefficient, the multiplication of this coefficient to this matrix. we're going to have Ka, and we can find its inverse, and normally that's going to look like 2k 2k, just because along the main diagonal we have the same entry, but along the back diagonal we're going to have the inverse. So we multiply by 1 in this case, and that's how it's going to look. All right, so this actually is equal to this inverse of this product with the coefficient k is equal to 1k over a inverse. So if we, for example, do the inverse of the coefficient k times, we have seen before there is a property that does not allow us to do it like this, but we have to change the places. So I guess it's going to be A inverse times K inverse, so which will give us also the same thing. Now here I see that it doesn't matter actually, because K is not a matrix with, you know, a number of rows and number of columns. It's just a kind of a constant, so it doesn't matter if you put it at the beginning or at the end. So you put it on the right or on the left, it's still going to give you the same result. So that's about powers of matrix, and we're going to proceed with some examples. So let's say we have matrix A 1 2 1 3, and that we have found its inverse, which is 3 minus 1 minus 2 1, of course. So we have this, and now if we want to have a to the power of 3, we have to multiply the same matrix 3 times to itself. So we have 1 2 1 3 times 1 2 1 3 times 1 2 1 3, and we can do that, of course, by using a linear combination, and in the end we will end with something like, let me give you the final result. I think here it's going to be, I think it's going to be this. Yep. So that's A, the matrix A to the power 3. So we have now learned how to do addition, subtraction, and multiplication of matrices, and we have also done the inverse of matrices. We have found the trace of matrices, and we have found the transpose of matrices. So at this stage we are able to solve polynomial expressions involving matrices. So we are almost at the end of this video, but let's start quickly. It's not going to take much time anyway. So we have polynomial expression involving matrices. involving there's something missing here, sorry. Okay, so let's say we have the polynomial, which is a function of, so px is equal to 2x to the power of 2 minus 3x plus 4. So this is the function that we have, and we have also the matrix minus 1, 0, 2, 3, and we are asked to find the solution set of this function for this matrix. So actually we know that the matrix A is composed of two equations. So we have equation 1, equation 2, and here we have another equation. The thing is that let's say we have the plane y against x. So we have two lines because we are dealing solely with linear equations. So we have two lines which are entries in the matrix A. But here the function px is a quadratic. So it's not a line, it's a curve. So by putting the values of A into this function, we actually, to my understanding, we are actually what we're doing is that we are looking for the point of intersections of the two lines with the curve. So the result should look like a matrix as well, a square matrix in that case, and it should give us some entries. But are they the solution set? Are they the point of intersections? I cannot say, unfortunately. So, but anyway, this is something that I will find out, and I will probably come back to this in another video. So let's proceed. If we want PA, so px, we replace x by a. X is equal to a. So we are going to have 2a to the power of 2 minus 3a plus 4. So to get rid of, here we have a constant. So what we have to do is multiply the constant with the identity matrix I. So which gives us this type of expression. And so now we have a square. So if we calculate a square, we just have to do a simple matrix multiplication or matrices, sorry. So how do we do this? Let's try together. And we have minus 1, 0, 2, 3 times minus 1, 2, 0, 3. So we can still try with the linear combination, and that's going to be something like this. 1 second. So minus 1 times minus 1, 0, and plus 0. No, it's going to be 2. Oh, this one. So we have a to the power of 2, and using the linear combination, we have this times this. We're going to get this, and then we have this looks like minus 2, and then we have 0 times the same thing, plus no, it's not correct. I'm going to erase this. This is plus, it's going to be 0 here, and here is going to be 2. So sorry about this. And so here is 2 plus we have minus 1 0 2 3, and this is 2 3. So I'm just going to give you the final result since I'm in a hurry right now. So this is going to be 1 0, and here it's going to be 4 9. So you can rewrite this. Once you have done this, you can do the next step. So as we can see in the function, we have to multiply by the coefficient 2. So we take this, which gives you 2 here, 0, 8, 18. And after that, separately, we have to multiply the matrix A by 3. So this will give us minus 3609. And you work your way. Here is another important moment when you will use the identity matrix. So here we're dealing with a 2 by 2 matrix. So we're going to use 1 0 0 1, and if you multiply by the coefficient 4, you get 4 0 0 4. So in the end, you will have something like this. You have the function a is equal to 208 18 minus 3069 plus 4004, which is the product of the coefficient 4 with the identity matrix. So the final result is this. Alright, so which brings us to the end of this video. Thank you for watching, and I'll see you next time. Take care. Bye.